Yes, Luiz and I are going to talk to you about DataFlowTasks, which is this package that we've been working on and off for, I think, 2 years now. And we just released version 0.2 because this conference was the occasion to mark a milestone. And we think it's ready for public consumption, so maybe you'll want to try it after this talk. So what this does is that it helps you express parallelism in a task-oriented way. If you know about things like StarPU or Parsec, which are task-based parallelism frameworks for linear algebra, these were kind of inspirations for us. But we do not have the same ambition because we only target multi-core shared memory parallelism on CPU. Okay, so it's less ambitious, but we do have the ambition to have a simple API, which is not really the case for StarPU or Parsec. And so as a preview, if you had this sequential code, like these 4 lines that are meant to represent some things you might want to do, and they would be performed sequentially in regular code. And in order to parallelize it with DataFlowTasks, what you need to do is only to prepend an @dspawn macro in front of each task. So this means consider this as a task that you spawn and will be scheduled. And in order to infer the dependencies from task to task, you only need to express how each task is going to access the data it works on. Okay, so you just tag every data with these write or read or read-write labels. Okay, and DataFlowTasks will then build a directed acyclic graph from it. And the hope, or the reason why you would want to do this is because, for example, these 2 lines, they don't operate on the same part of the array, and so they can be performed in parallel. And so you want to gain speed up from that if you're in a multi-core shared memory setting. Okay, so that was the broad idea. And now we're going to, in the first half of the talk, we're going to try and express more clearly what task-based parallelism is, when you'd want to use it, and when you'd want to use DataFlowTasks to do it, and how it works under the hood. And then Luiz is going to present this much larger use case where we implemented tiled Cholesky factorization in parallel using DataFlowTasks, which is a nice example because we can benchmark against implementations like OpenBLAS. Okay, so first an introduction. Again, the idea is for now to look at a very simple example, which is not useful in itself, but it just shows how an algorithm could look like, where you first create some data and initialize it, and then maybe you work on 2 different parts of your data, and in the end you do something with the whole array again. Okay, and in this context, what we're going to call a task is one atomic part of your algorithm that's going to run in some thread and hopefully not be interrupted. Okay, and the dependencies between the different parts of your algorithm will be based on tasks. And we really rely on the base tools that Julia provides for us. So there is a notion of task in Julia, an object that you could create using this @task macro. And usually you don't go so low level because you want to create the task and also schedule it, which you do usually with this threads.addSpawn macro. But I mean, we rely on this, and Julia already provides all the tools we need. The only thing that's left for the programmer to do is, once you describe each of those tasks, you have to synchronize them. You have to tell Julia that these two tasks, because they work on data that's been initialized in the first task, you have to wait for the first task to finish before you can start tasks 2 and 3. And you have to wait for task 4. For task 4 to start, you have to wait for these two tasks. Okay? So that's what you need to do if you want to use tasks, and that's what DataFlowTasks helps you do. So if you had only base tools, one way to look at it would be, okay, I'm going to have a task that produces some data, and then this data is going to be fed to a subsequent task that's going to take the result of the first as an argument. And if you have an algorithm that's based on this producer-consumer type of things, then you can use fetch to say, okay, I'm spawning a task, and then I'm fetching its result, and as a consequence, because this task fetches the result from that one, it cannot execute before the first one has finished. Okay? So if you're in this context, which is like the easiest one, then fetch is a natural thing to do. And this is actually what things like Dagger do for you. Okay? They automate things like this. But this is especially nice to use when you have tasks that produce the data and tasks that consume them. Okay? And in this case, you see that something like this is not easy to do. Okay? In this case, we want to take the vector that we've been mutating in parts, and we want to work on it globally again. Okay? So there's not really a good way to say this task is going to take something from the two previous ones. Because semantically, these two tasks, we'd like them to mutate the data, not take some part of the array and create a new one. So if you have a mutating implementation, what you need to do, you don't really have things that are produced by tasks and consumed by others. You have tasks that all mutate the same data, and what you need to do is actually insert barriers saying, okay, I explicitly tell that this task has to wait for the previous one. Okay? And if you had to do this by hand, you'd have to know that this task has a dependency on this one, and the same for the third task, and this task has a dependency to both T2 and T3. Okay, so this would be your responsibility, to know the task-to-task dependency. And it's not always very easy to figure out what these dependencies are. In this case, it is, but it's not always the case. And as Luiz will demonstrate in the Cholesky factorization case, it's very hard. But what is usually easier is to express the fact that one task accesses some data with some mode. Okay, so it's kind of easy when you write this to know that B is accessed write only, or in this case that B is accessed, the first half of B is accessed read write, or things like this. And so the idea behind the data flow tasks is to take these tasks plus annotations that you as the developer put in front of your code. And when you say, okay, this piece of data is accessed read-only or write-only, then it allows DataFlowTasks to actually infer for you the task-to-task dependencies. So this is actually what DataFlowTasks helps you do. And the way it does this is actually quite simple. Okay, so we wanted to show you this because there's no dark magic inside. You could have actually written it, but it's just that it's done for you and it's nice to use. So if you create some data, B, it's an object that lives within the Julia space. And afterwards, if you spawn a new task with DataFlowTasks, with this main API, which is the @dspawn macro, you actually declare a write dependency from this task to the data B. And for now, there's nothing else to do because there are no other tasks. So that's it. But when you create a second task, it declares also its own data dependencies. In this case, it creates a dependency to a view of the same array, but only the first half. And these are two different objects for Julia. Okay? There's one object which is an array, another object which is a subarray. And we have to know, if we want to know whether there's a dependency between 1 and 2 as tasks, we have to know whether there is an overlap in memory between those two Julia objects. And there's a function, a function within DataFlowTasks that's called memory overlap. You can overload it with new methods if you like, but for now it supports a lot of methods for linear algebra, for example. And this method say, okay, you give me two objects, B and a view on it, and I'll tell you whether they overlap or not. In this case, they do, because the subarray is a view on the original array. And so there actually is a dependency between those two tasks. So we are going to register it in the directed acyclic graph. And then when we spawn a third task, it depends on yet another Julia object, which is another subarray. And we can try and see whether there are dependencies between task 2 and 3. And in this case, we examine the overlap between these two pieces of data, and there's no overlap because there are subarrays of the same array, but with different indices. So it's fine, and there's not going to be any edge, any dependency between those two tasks. But when we examine the dependency between 1 and 3, then again there is some overlap in the data, so we have to put a dependency there. And this goes on. If we now add the fourth and final task in our graph, then we do have a dependency between 3 and 4 because the data overlap. We also have a dependency between 2 and 4. And when we come to examine the dependency between task 1 and task 4, we already know that there's a transitive dependency because of tasks 2 and 3, so we don't even have to examine this new dependency, it's already there. So that's actually more or less all there is to it. That's how we build a directed acyclic graph to represent the dependency between all those tasks. Just note that each task you introduce has to try and see whether it has dependencies with all previous tasks, meaning that overall the complexity of inserting all tasks, of inserting n tasks in a graph will be quadratic, okay, with respect to the number of tasks. So we have to make sure that this insertion is kind of efficient. Once we've done this, and here I'd like to emphasize that the task scheduling happens each time a task has been created, okay? So I'm presenting it last for the purposes of the presentation, but as soon as this task was created, it has been spawned and scheduled, okay? And so when we come to spawn this task, we already have scheduled all the previous ones. And the only thing we have to do now, after having created this fourth task and inserted it into the graph with the correct dependencies, then the only thing we need to do is to actually put the correct waiting calls before the actual work in order to make sure that the regular Julia scheduler will wait for all the dependencies to finish before it starts doing the real work on the real array. Okay? So again, the takeaway from all this is task-based parallelism is a way to express parallelism in your programs or algorithms by defining some tasks that depend on one another. The use case for DataFlowTasks is when you want to have task-based parallelism on algorithm that work in place. So they don't have this producer-consumer thing. And the idea, as we just saw, is just to, on the fly, try to infer task-to-task dependencies from the task-to-data labels that you write on your code.
So for the this is working. For the second half, I just want to present a more complicated example where so far we've seen things that you could just by hand add a dependency into these tasks, and I'll talk about the tiled Cholesky factorization algorithm, and I'll try to illustrate all of the tools that we have in place so that you can profile, debug, and also compare the performance of this example with, say, OpenBlast. Okay, so just to give an introduction to the algorithm, so essentially a Cholesky factorization is you take some matrix, which is symmetric, positive, definite, and you try to decompose into a lower triangular and its transpose. So it's like the LU, but for SPD matrices, okay? And to get the idea of the tiled algorithm, I think it's good to just look at the 2x2 case. It's very simple. If you have a, if you have a 2x2 block matrix, and you just write down what each equation here does. The first one just says that A11 is just L11 and L11 transpose. So this is exactly a Cholesky call. Okay, it's exactly what you're trying to do. And then you write the equation for the A12. So after you solve this, you actually computed L11. So you can just do a triangular solve here to find L21. Okay? And you can do all of that in place, of course. And then if you write what the block equation is for the A22 block, you have to sort of do a Shrew complement here. And then you have to do it. So this is the first step. You have to do like a matrix multiplication. And then you have to do a Cholesky again. So here we can't really parallelize anything because it's just the 2x2 block. But let's just look at a bigger case now, okay? And I'll try to illustrate how the data kind of moves through these. And the point is that for efficiency, so one thing that maybe we didn't say is that a lot of these linear algebra algorithms, we want to do as much in place as possible. So we want to have a function that just takes data and works in place and does not allocate, okay? So the goal will be to compute this, and the first step, so I'll just describe the algorithm. I just need to look at the lower triangular part of this matrix, and the first step is I'll do a Cholesky of this block, and at the end, the green block is now written, so I overwrote the matrix A, where this green block is just a Cholesky decomposition of it. And then, so after I've done with the data here, I've written in place, I can then move and do these lower triangular solves, okay, to fill in these orange blocks. And again, this would just overwrite whatever data was here with that. And then after that, the third step, there you go. So after we've done that, we can then just do this multiplication, okay? Which was what I showed in the previous slide, this matrix multiplication. And then we're done with this first column. We just move on to the next part and we continue. So if we're doing this so this could be a point where we just synchronize a sort of fork join place. So if we wanted to write this algorithm by hand and not use a DataFlow task, we could have written by hand the first set of dependencies, so that wouldn't be very hard. And then we just join here, so we just wait for everybody to finish, and then we work on this blue part now, okay? And the idea of DataFlow tasks is that you don't have to synchronize it here. You can just continue spawning tasks. And for instance, this block over here, I can do a Cholesky of this block way before I'm done working on the first on the entire first column, okay? Because if you remember, this was a Cholesky here, and then there was an LDiv, and then I do a mul. So I can start working on, so you expose parallelism faster, okay, if you do something like that. And at the end of all of these iterations, you've just written A with, so the lower triangular part of A contains this L that you search. So now to show, so to talk about what is the complexity of this, so it's a BLAST 3 problem, so this is a cubic complexity problem. And you can look at what we have done. So for each one of these columns, we did one Cholesky. So we have order n factorizations. We have order n square triangular solves. And then n cube matrix multiplications. And this is a good example to sort of showcase, because this is really compute bound problem. I mean, you have n square data, and you're doing n cube operations. So you can sort of hope to gain some performance by doing proper parallelism. Okay. So this is what sort of the code, the Julia code would look like for the algorithm I just described. So this is all in place. You loop over every column if you want. You do a Cholesky of the diagonal block, and then there is this LD, so triangular solves and the mules in here. And the point of this, so this is relatively simple Julia code. And the point was just to show that if you want to parallelize this with DataFlowTask, you just have to reason very locally about how each of these kernels that you have, so you have 3 kernels here, Cholesky kernel, LDIV, and mul. You just have to reason very locally how they depend on the data, and not how they depend on each other. And as we'll see later, the task graph that is generated is actually quite complex, okay? Because there are dependencies that are very difficult to foresee when you go through this algorithm. So I think that is sort of to illustrate, and now we just benchmark. Let's just do sort of a simple benchmark here to see how it performs. So we have this Cholesky tiled problem, and we run so for matrix of a certain size. And we can see here that on 8 threads, for example, on some hardware, it's not too important what it was, we gain a speed up of, say, about 5. Is this reasonable or not? So that's a sort of a question you should ask. I mean, can you do better? So to try to understand whether this speed up is a good speed up, we have some tools to help you profile and debug this code. So to profile the code, what you have to do is there's this @log macro. Okay, so you have some function that spawns data flow tasks, and if you run it within this @log macro, we'll start. So each task will start recording some of the information that it needs to later process this DAG and later show when it executed. One important thing to keep in mind is that this is when it's disabled, it's no cost. So essentially, the @log does an eval inside that defines some function. So maybe the code has to be recompiled every time you turn it on or off log. But when it's off, there is no cost to the login. Okay, and then there are several ways which you can query or inspect this log info object that is returned. The simplest one is just sort of a REPL way where you can ask it to describe. And I will not go into these categories right now because we have a better example. So if you're willing to use, say, Maki for the plotting, we can plot some other nice stuff. So the good thing here is that you don't need any external dependencies, okay? Okay, so one of the things that you can do with this after you've logged it is you can look at the task graph that was actually created, okay? And if you have GraphViz installed, okay, or you don't have to have GraphViz installed, we can set up this stacked environment for you if you want, but you could just have your own GraphViz if you prefer that. You can plot the DAG that was created by this, and you imagine like if you had to spawn all these dependencies by hand, it's not that trivial of a structure, okay? The algorithm that I just described, it's complex enough that makes it difficult to really describe how tasks depend on tasks. So the whole point is it's simple in this case to describe how tasks depend on data. Okay? And then the other thing is if you have a GL Maki or Cairo Maki, we can then visualize this. We can visualize the parallel trace of what tasks are executed. So if you remember, probably don't remember because I didn't say, but every time we spawn a task, we gave it a sort of a label. And this label was just used so that we can later group tasks and see what takes what time. And this is very good for inspecting and trying to understand, you know, what does your algorithm do. So here is each one of the threads, the time, and we can see the tasks, how they get executed. So if you remember, the the chol is the one that actually unblocks the LDIVs, that then unblocks the muls, and then it goes all the way. At the end, we are sort of limited by this graph. It narrows down again. Okay, so there are a few important information here. So I think this one just speaks. So this is for the time you spend computing and the time most likely you spend waiting. Okay, just idle. And the important stuff here is these two in this middle plot. You have these two lower bounds on the time. So to know if the algorithm was properly parallelized or not, you could look at these two lower bounds. So one of them is just a no wait type of bound. You just take the time that so you sum the time that all tasks took, and you divide by the number of threads that you had. So in some sort of embarrassingly parallel algorithm, you could do something like that. Okay, so that's the best case scenario. So this is a lower bound. So it doesn't take into account the structure of your DAG. And the other lower bound that you can do is you now look at your DAG, and you suppose if you had infinitely many tasks, infinitely many threads, what is the best that you could do? And you can do no better than what is a critical path. Okay, so this sequential path. So these are sort of two good indications. Should I increase the number of threads maybe, or what should I do to make this problem better? And then you can just look at locally what each one of these types took. And if you were to optimize something, probably they should complement. So this mul part is what you should optimize. Okay, so just to wrap it up, I think this was a good example because we can sort of compare it to OpenBlast. And so if you compare it to OpenBlast, this is we do comparably well, let's say. So this is multi-threaded, 8 threads, and the kernels that I showed there, this shol, ldiv, and mul functions, they actually calls to they're calls to OpenBlast. So you could have written these kernels in Julia yourself if you wanted. What we handle here is how you actually parallelize this, and yeah, so it performs, I think, reasonably well compared to say OpenBlast. And so this is just the time and the gigaflops. And then finally, so for this example, if you have a sort of a bigger, as you start to make this problem bigger, the task graph, the parallel trace, you can see that when you actually start spawning lots of these small tasks, you can fill up most of the work, okay? And for example, here, we have a time which is, so the actual time that took is kind of comparable to if you had an algorithm that you could just run everything. So the bottlenecks that we saw for the smaller case, they start to disappear for the bigger case. And I think that is the end. So some concluding remarks. So our goal was to sort of express parallelism through these task-to-data dependencies, and in the research I do, the algorithms tend to be kind of close to what I showed here in this Cholesky case, and it turns out that this paradigm of describing how you access data is a very convenient way of expressing parallelism. We really wanted to focus on a simple API, so there is one exported macro, so it's just at this spawn, and there's nothing else. There are lots of examples actually for the 0.2 release. We focus a lot of like showing, so there's examples of merge sort and maybe like simpler algorithms. So there's longest common subsequence, things like that we show how to parallelize it. And yeah, that's it. So if you think the algorithm is complex enough, so it has to be complex enough so that you cannot just do it by hand. Because if you can do it by hand, the overhead of creating a DAG and doing all of that is probably not worth it. Okay, at least you don't need it. So the overhead is not too big here. We've made all of that relatively efficient, and we can see that in the Cholesky case, for example, there was I think I even had, yeah. So this task insertion is like how much time did it take for me to put these nodes into the DAG, analyze them, clean up this DAG. All of this has to be done in a thread-safe way. So there's some locks in there, but you can see that this is not a big factor of the time. Yeah, so that's it. Sorry, oops.
Yeah, so I think we have time for some questions, something like that. So if you have a question, ask if you can repeat the question, because then it's also on the recording. That would be awesome. Yeah, go for it.
Yeah, thank you for a nice talk, and I will try that with your package. But I have a question. What do you think would you able to do it in the future, or it's possible at all to make even overhead on developers smaller, to kind of have a macro dtask that will put all this read write for me in my code? Because I can imagine in some cases it's inferable from a code. For example, if it's a view, I know that I will not write in this write in this part of the code. Kind of like, can we use Julia compiler to help us to make this burden from me? And also, why I'm asking it, because I'm working a lot with codes that generated, so I cannot kind of prescriptively say where to put them. So because I don't know what code actually will be run.
répondre? Yeah, so the question is, can we infer these tags and the data accesses in tasks? And the short answer is it's very difficult to do so, and maybe even even this shows why. Because when you call this fillBang function on a vector b, the compiler doesn't know that fillBang is meant to write to your array and I mean replace all values with zeros. So at some point when you're calling a function, you have to know the semantics of it. So maybe we could have like a library of known functions for which we know what they write and what they read and so on, but we can't do this reliably on all user code.
Yes, just what in some earlier version of this package, we actually had a sort of dictionary that would map certain like known functions to how they access each one of their arguments. But even the name is not enough because you could have mul can take 3 arguments, or it could take 5. So you have to say that I know exactly that if you do a mul bang, the first one is accessed in this way. And they just start having this dictionary that has to be extended by the user. So it didn't seem like yeah. So it was motivated. I work with something called hierarchical matrices, which have a structure which is a bit harder than this. I didn't have the time. I mean, I wouldn't have the time to explain it here. Yeah, so I work with the just the H one, so not the H2 ones. But in there, you want to do LU factorizations, and this is almost a must. So if you don't do something like that, if you try like a fork join approach to the LU, performance is horrible. And the structure there is way harder. You cannot really easily infer dependencies between tasks.
I also worked on HSS.
Yeah, yeah. So I have this implemented in some other package. I have an H-matrices package that this is how I do the LU, threaded LU, is done by this package now, actually.